Hello everyone, today I'm going to talk about Einstein's biggest blunder. What's a blunder? Let's get started. So Einstein, after he came up with the general relativity, he came up with Einstein field equation, so-called Einstein equation, which is written here. He told us on the right side it's a matter, gravity, and then on the left side is space, curvature of the space. And he told us that matter, if there's a matter in the universe, there's a gravity, and the gravity is going to bend, curve the space-time on the left side. And then if the space is curved, the object is going to follow the curved space, curved path. So Einstein told matter told space how to curve, and space tells matter how to move. So this is what Einstein equation tells us. But when Einstein came up with this equation, he noticed because matter, most of the matter in the universe has a gravity, and the gravity is a pulling force. So much gravity in the universe, gravity is going to shrink the universe, and eventually universe is going to get smaller to the big crunch. But in 1920s, when Einstein came up with this Einstein field equation, people, including Einstein, believed the universe is static, meaning not expanding or not shrinking. It should be stable forever. So Einstein thought this equation may be wrong. And then Einstein tried to fix his equation and then put the so-called cosmological constant into his equation here to balance the left side of the equation and right side of the equation to stop the shrinking of the universe. So now to counteract the matter, gravity from the matter, he needs this new term, so-called cosmological constant. And then he published a paper. But later, in 1929, Edwin Hubble discovered the expansion of the universe. So this is the plot from Hubble's original paper. So what it's saying is this x-axis is distance from the Earth, and individual these points are each galaxies. And then y-axis here is a velocity, recession velocity of these galaxies. So these galaxies are moving away from the Earth. The Earth is in the Milky Way galaxy, so other galaxies outside of the Milky Way are moving away from us. And then what this Hubble's plot is showing is that more distant galaxies are, their moving speed, recession speed is faster. So this is so-called Hubble's law. What this means? This is indicating our universe is expanding. Let me show you in this way. Here's a balloon of the universe, and then there are galaxies inside. And then if I make this universe expand, then the distance between each galaxies are getting far away, right? So the galaxy, if you look at from one galaxy point of view, the other galaxies are moving away from you. Exactly just like Hubble found. And then moreover, the galaxies further away. For example, if you're this galaxy, and then this, if you're this galaxy, and this galaxy is moving away from you, but this galaxy even farther away are moving away from this one and also away from ours, so moving almost twice as fast as this galaxy. In this way, if the universe is expanding 3D, then the more distant galaxies are moving away from us faster. So this is what Edwin Hubble discovered. Okay, so Einstein heard about Hubble's discovery and he was so pleased. Einstein learned, okay, the universe can change the size. So his equation was correct in the original form. So he was so delighted to learn about Hubble's discovery of the expansion of the universe, and then he removed this cosmological constant from Einstein's equation. And then now Einstein's equation is in the original form, and then universe can expand or shrink, it can change the form, and Einstein was so happy. Then Einstein called himself adding this cosmological constant was the biggest blunder in his life, because his equation was correct in the original form. Now Einstein was so pleased, so he personally visited Hubble to the Mount Wilson Observatory in California in 1931, and this is Einstein looking into the Wilson telescope, observatory telescope, and this is Edwin Hubble, and he congratulated Hubble for his discovery. So this is a general story of Einstein's biggest blunder, but the story did not end here. More recently, two teams who received the Nobel Prize in 2011 used supernova explosion to map the expansion of the universe. So this is a supernova explosion here. It's bright. Supernova explosion is very, very bright. It's just explosion of one single star, but it's as bright as its own host galaxy. Host galaxy has 100 billion stars in it, but one single explosion is as bright as 100 billion stars. So because this supernova explosion is very bright, we can find the supernova explosion in very distant universe. And then more importantly, we know the intrinsic brightness of this supernova explosion, because this type of supernova, it's called type 1s supernova, explodes at the Chandrasekhar mass. The mass, explosion mass is always the same, so the brightness is always the same. Then, if the brightness is the same, we can use it to measure distances. Just like a candle shown here, if we know the brightness, and then apparently it looks faint, then that means that supernova is far away. If apparently the supernova looks bright, then it's in a nearby universe. So this way you can measure the distances to those supernova explosion and its host galaxies. And here's a result, how they measure the expansion of the universe. So as a function of distance, and this is the brightness of supernova explosion, and these individual points are supernova explosion. What they found is that those distant supernovae are little bit fainter than expected. You know, this curve is points a little bit above, right? It's just a tiny bit, but they are fainter. They are fainter. Why? They are fainter because universe is not just expanding, but this expansion speed is accelerating. So this is a discovery of the acceleration of the expansion of the universe, and in this acceleration was dragged by so-called dark energy. So this is discovery of the dark energy. So that's why these three gentlemen received the Nobel Prize in 2011 by finding the accelerating expansion of the universe. So let's go back to the Einstein equation. So to make the universe static, Einstein put this term cosmological constant. But later, when Hubble discovered expansion of the universe, he removed this cosmological constant. But nowadays, we need this cosmological constant again, not to balance the gravity, not to make the universe static, but to make the expansion of the universe accelerate. To accelerate the expansion of the universe, we need this term, larger value than Einstein put it in. We need this cosmological constant to accelerate the expansion of the universe. So that's why Einstein's biggest blunder, to take this away, was a blunder. Einstein's equation was correct before he took away the cosmological constant in this form. This is how genius Einstein was. And then researchers nowadays including myself, are trying to figure out what is this cosmological constant. It's a remaining mystery in the universe. Okay, I stop here today. See you next time.